Okay, so today's class is going to be on the topic of divisibility and something called remainder bounding. So at any time, please feel free to ask questions or any doubts if you have any, and preferably unmute and speak, although you can also ask on chat. So today we'll be looking at certain problems which use the idea of that if you have A divides B, then that means that the absolute value of A is less than or equal to the absolute value of B. So this might be very intuitively obvious, and you can see the reason also, right? Because if you're saying that A divides B, then now just forget about the sign. Let's just think that both of them are positive. So that just means that you have a lot of A's and they all fit in some B. So that obviously means that the absolute value of A is less than or equal to the absolute value of B. Because, yeah. Also, there's the case when B is 0, because like you can say that everything divides 0, and that means that there are none of A's. So certain problems use the idea of, say, if you have some A divides B, then you can also say that A divides B minus A. Like you can keep on removing blocks from this thing. And suppose eventually you get something very small on this side, like you're saying that A divides something very small. So that means you kind of have a contradiction, right? If this thing is smaller than A. So then that would imply that the thing on the right side must be 0, because otherwise A cannot fit into that. So many of the problems are going to be using that idea. So let's just start with a simple problem which uses this. This says that A square B minus 1 divides AB cube minus 1, and AB are positive integers. So just try to use the ideas I said above and try to approach this problem. And if you have any ideas, you can say. And also in general, a strategy which you can use to try to reduce the right hand side as much as possible is you try to like get rid of a certain like big term on the right side. So for example, here, if you want to get rid of AB cube, you can't directly subtract anything from the left side, but you can say that A square B minus 1 divides AB cube minus 1. And you somehow want to make this term similar to this one. So you just multiply this whole thing by A. So you know that this divides A square B cube minus 1. And from this, you want to subtract something times A square B minus 1. Like you know that A square B minus 1 will divide this minus any multiple of A square B minus 1. So now if you multiply this by B squared, and then you subtract it, then here this will be equal to.
Just a second. It should be a square b cube minus a, na? Because you multiplied the entire thing by a.
Yeah. A square b cube minus. Yeah, so here you're essentially getting rid of this term when you're subtracting this. So try doing something like that and try getting some conditions.
I, I think I got some answer.
Okay.
I'm not sure. Is it like it should be either some like a comma b is some zero comma some other integer like any integer, or yeah, or something like a some integer comma zero, or it is like
Okay.
a comma a square, or it is minus one comma minus one. But since it's positive, that's not possible. So yeah, only the first three things.
Okay, so how did you get this? Like, did you use the inequality?
Yeah, kind of. So like I just so like if a squared b minus one divides that RHS, so it should also divide a cube minus one minus a squared minus one, a squared b minus one there.
Yes. So okay, on the RHS, what did you get? B square minus A?
No, like a yeah, so a b cube minus a squared b,
Yes, yes, that's correct.
and so like you can say from there like so it also divides a squared b minus a b cube. Can you say that like
Yeah, so you took
so?
AB common, right? And you know that this is co-prime with AB.
Yeah, or like what I did was so since it divides this, so it divides like a squared minus b a squared b minus ab cube too.
Yes, that's true.
So if ab cube was greater than 1, it wouldn't be possible because it would be less than a squared b minus 1.
Yeah.
Yeah,
So you're
so
saying it
it
should
should,
be,
so the whole thing should be 0 or ab cube should be 1.
wait, so you're saying this must be the case, right? Are you saying this?
No, like I'm telling that, yeah, a squared b minus ab cube is greater than or equal to the other way around.
Okay. Yeah, this is not possible.
Yeah, so ab cube should be less than equal to 1. So it's either 0 or 1. I mean, the whole thing should be
Okay, but you can
0
also
or 1.
have that this is positive, right? This could be positive.
Okay.
Like you're
Oh,
looking at the
yeah, then
absolute value.
okay, I have to check that case. One.
Okay.
I got something, but it does not work for a less than b, maybe.
Okay, what are you getting?
Like we will get a square b minus 1 divides b square minus a.
Yes, correct. Because you know it's co-prime with AB because AB
Yeah,
divides this thing. Yes.
yeah. So this that means that one thing, if you observe that if a is greater than equal to b, therefore b square minus a is always less than a square b minus a. So it's not possible. So therefore
Yeah.
b square a minus a must be 0. So a equals b square.
So yeah, one case is A equal B square, and you can easily check that this works. Now, suppose B square greater than A.
Like if b is greater than a, that's where I'm facing a problem. Like I cannot
Okay.
I cannot say that a square b is less than greater than b square just like that. If a is less than, if b is greater than a.
Yes, so maybe try to do something with this expression and maybe try to reduce it further somehow.
Yeah, I got it.
Okay, what did you do?
When you again, let's do the same thing. You will get
Mhm.
a square b minus 1 divided b minus a cube.
Okay, so I'm guessing you did something like this.
A, yeah, like that.
Okay.
Like in my b minus a cube. Now, see observe one thing that this implies a square b minus 1 is less than or equal to a. It's like first of all, you subtract it, right? So if you
Yeah, you do
subtract,
this.
yeah, we do that. So we will be getting b minus a cube. This is given b minus a cube, right?
Yes.
So this must be less than or equal to that.
Yeah. B minus a cube or a cube minus b.
Huh?
Like it could be either way. Right? Like you still have two cases, but yeah.
No, no, like if from here we done, I guess, because a square b minus a square b is greater than or equal to b. First we write like that, a square b is greater than or equal to b.
Okay.
And 1 is less than, means a cube is greater than or equal to 1. If you can see, yeah. So if we add those inequalities and shift the signs, we will get that a square. Yeah, yeah.
Okay.
We add those equalities and we get that a square b minus 1 is greater than or equal to b minus a cube, and hence a contradiction.
Yes, but there's also if a cube minus b is positive, right?
Huh?
Yeah, but you already showed that a is less equal b before. Like, okay, you already showed that b minus a cube cannot be positive, but what if a cube minus b is positive? Like, what if you need to show this?
Uh, okay, this. Yeah. Yeah, so from here we know one thing that b is greater than a, so we can write a
Exactly.
square.
Yeah.
Yeah, b is greater equal to a.
So
No,
yeah, this cannot be positive.
yeah, yeah, yeah.
Okay,
Okay.
so there's also the case when this is zero. So in that case, you
B
have
equals a cube.
a cube equals b. So we have a equals b cube and a cube equals b, but also uh, I think there's one more solution when you have like 1 comma b. Like I don't think. Okay, so suppose a cube minus b is positive. Wait, how did you show that a less equal b?
Yeah.
When you show that a less equal b, I think there was one more case when a
No,
equals 1.
so we took two cases, right? A less equal to b and a
No,
no, we first took a greater than equal to b and then we took a less than b. So a greater than equal to b gives a equals b square and a less than b gives a cube equals b.
yeah, okay. I think the case we are missing is if minus 1 is equal to a cube, right? Because over here, so if a is exactly equal to 1, then this doesn't work. But then like 1 comma b works anyway. So yeah, there are 3 solutions.
Got it.
Okay. And it's very easy to check that they work, so I'm not doing that now. Okay. So this is a very similar problem, but slightly difficult. But it uses the same kind of ideas. So yeah, you can try.
आगे बढ़ गए।
So initially, maybe we can try to forget about this condition. Maybe it'll come up later. So now just focus on the fact that you're basically saying that a square plus b plus 3 divides ab plus 3b plus 8. And try to use a similar kind of thing here that we just did before, like reducing the RHS.
Like I got like a squared plus b plus 3 divides a plus 1 whole cube, but I don't know how to proceed from
Yes.
there.
Okay, so that's very close actually. So I'm guessing you subtracted. So here you have a plus 3 times b plus 8, and now you want to get rid of the b, right? So if
Yeah.
you just subtract a plus 3 times this, then here you get a cube plus, if you cancel everything, like you'll get 9 here, which cancels. So you'll get the negative of this, and this is equal to a plus 1 whole cube. So now you have that a square plus b plus 3 is not divisible by the cube of any prime, right? And you're also saying that it divides this thing which is a cube. So since you know that it's not divisible by the cube of any prime, can you reduce this to something smaller in a different way, like just using the primes? Like try to think about that.
A square plus b plus 3 divides a plus 1 whole square.
Exactly. Because if you know that if any prime comes 3 or more times in this, that does not really matter because this cannot have a prime power greater than or equal to 3 because it is not divisible by any prime cube. So you might as well just say that it divides a plus 1 whole square. Because any primes that come 3 times are irrelevant anyway. You can just have them 2 times and that's fine. I hope that makes sense to everyone. If that part is not clear, please do tell. So now you have a square plus 2a plus 1. And from here, it should not be too hard. Can you see the
পর্বে
flash?
অর্থাৎ যেখানে ভিডিওটি একটি লঙ্গা তোমরা দেখতে পাচ্ছ নিশ্চয়ই 8 আর 30 মিনিট হয়ে গেছে। তো দেখো অতটাও বড় নয়। প্রথমে তোমাদের আমি প্রশ্নগুলি দিয়ে দিচ্ছি, এই প্রশ্নগুলি তোমরা ভালো করে নেবে।
No number greater than a square can divide a square plus 2a plus 1. No positive number.
No number greater than a square?
No positive integer greater than a square plus b plus 3 can divide a square plus 2a plus 1. And since b is positive, then there is no such.
Yeah, like an easier way to say that is from here you can just subtract a square plus b plus 3 because as I said, you can subtract the LHS any times you want from the RHS. So you just have a square plus b plus 3 divides 2a minus b minus 2. And now you have two cases, and it's easy to check that like either this is greater or equal.
I don't think like there are many values for which it is greater than equal to. I don't think there are any values
Yeah.
for which this is greater than equal to this.
Yeah,
Are there
because
any values?
if a is greater or equal to 3, then anyway this does not hold.
Yeah.
And if a is 2, you can just put it in and check, right?
A can be 1 or
Because-
2. Yeah.
Yeah, even a equals 2 doesn't work because this just becomes 2 minus b, and this is obviously greater than that. And a equals 1 also obviously does not work here. And in the other case, you have plus 2 minus 2a greater than this, which is also like obviously not true. So yeah, there are no such integers, and I hope this was clear to everyone.
Yeah, so we are done.
If we take
Yeah.
a equal to b equal to 2, we get n equals 2.
Okay, yes, that case is also there. If
Yeah.
this thing is 0, then we get b plus 2 equals to a. And then, yeah, I think if you just substitute it back in, so you get n equals 2. And that is your only possible case, because the only fact that we're using the inequality is this case, and here we checked all cases, like this can be 0 or greater or equal. And both of these are not possible, so it has to be 0. Okay. And this is a slightly different kind of problem. So like try this for a few minutes.
I guess it can also be done by that factorizing trick. Like we can
Yeah,
factorize it.
that is the idea here. Do you know how to do it? Then maybe give the others some more time.
I mean, in these type of questions, what we can generally do is like, wait, did I do? Like we can multiply all of them.
Okay, like directly multiply or in some other way?
Yeah.
How exactly are you multiplying? Are you doing
Like ABC divides BC plus B plus C plus CA plus C plus A plus means what I'm doing. ABC divides BC plus B plus C multiplied by CA plus C plus A multiplied by AB plus A plus B, and open them up and then try to continue.
okay? We can try that. So we can directly remove all the ABC divisible terms.
Can you multiply the first divisibility by a plus 1, the second by b plus 1, and the third by c plus 1? You multiply the RHS of it. And then you get a divides a plus 1 times b plus 1 times c plus 1 minus 1. And then you use Chinese remainder theorem to get a plus 1 plus b plus 1 plus a plus 1 times b plus 1 times c plus 1 is equal to 1 mod ABC.
Right, so you multiply this by a
No.
plus 1, right?
No, yeah, and you write b
Okay.
c plus b plus c as a b plus 1 times c plus 1 minus 1. You don't expand it. You write bc plus b plus c as a
Okay.
b plus 1 times c plus 1 minus 1. So we have a divides a plus 1 times b plus 1 times c plus 1 minus 1.
Yes. And you
And
can
we have the
simplify
similarly
those.
for b and c. So we get a plus 1 times b plus 1 times c plus 1 minus 1 is divisible by abc.
Yes, because you're given that ABC are primes, so like nothing can be in common. That's why you can say all of them are dividing. Okay, now you have to expand, right?
And yeah, you expand. So you get that ABC divides AB plus BC plus CA plus A plus B plus C. And I think from there you can do some size.
Yes, so okay, so you're given that these are distinct prime numbers, and if any one of them is 2, then you are given, then you get that 2 divides BC plus B plus C. Now you know that they're distinct, so B and C cannot be 2. B and C are both odd. So then you get this is odd, and this is odd. So this whole thing is odd. So 2 cannot divide an odd thing. That means that none of them can be 2. That's like some basic thing you can always check when given primes. You can check if you can eliminate the even case somehow. So in this case, 2 is eliminated. So you know that all of them are odd. So the smallest case you have is 3, 5, 7. And if you're putting this in, also like you can remove the ABC from here because of this ABC divides ABC. So if you put in 3, 5, 7, then you'll get this as something like 105, and this won't be big enough. This is 15 plus 35 plus 21. Yeah, so this is smaller than this. And now notice that if you're increasing one of the primes, if you're increasing A, then the left side terms ABC increases by the amount you're increasing A. So if you're increasing A by say some K, this increases by K times BC, but the right side just increases by K times B plus C plus 1 because of the terms dividing A, the terms which A divides. So if BC is greater than B plus C plus 1, then you know that the LHS is always increasing. So it's always going to be bigger. So the only case you have is when BC less than or equal to B plus C plus 1. Actually, it's just less than because you already know the LHS is bigger. You just want to prevent it from getting bigger, from getting smaller. So you can write this as, and this is just a few cases which you can check like. So this has to be equal to 1, and that's not possible because none of the primes can be 2 as we already showed. So from this step onwards, it's just checking the size of the primes and making sure that ABC is always bigger than this. And that's sort of intuitive because ABC is a 3-degree term. So as the numbers get bigger, it should always remain bigger. and you just have to do a few cases to make sure that happens.
How do you get BCA is less than B plus C plus 1?
How do you get what?
BC is less than B plus C plus 1.
No, you're trying to prove a contradiction to this. Like you want it to be greater than B plus C plus 1, because then you can show that the LHS always remains bigger, no matter how much you increase one of the variables. That's what we're trying to show. Like suppose you're increasing A by some K, then LHS increases by K times BC because of this. But RHS increases by K times B plus C plus 1. So the only bad case is when this happens, but this is equivalent to this, which is a contradiction.
Okay.
Okay. I just say if it's not clear. So I hope that's fine. And yeah, so this used to
Can you
kind of
repeat after you prove that ABC divides AB plus BC plus
okay.
C plus
Okay, sure. So you know that this is the smallest case possible, and this case does not work because ABC is too big. So now on the LHS you have ABC, and on the RHS you have AB plus BC plus CA plus A plus B plus C. So now you want to show that if you increase one of the variables, you want to show that the LHS increases more than the RHS. Because then you can say that no matter how much you increase any one of these, the LHS always remains bigger. So you want to show that how much ever you increase, say A, then the increase on the LHS is more than the increase on the RHS. So showing that would finish. That's the first thing. Is that clear? So now if you're increasing A by some K, like suppose you're taking A and making it A plus K, then the increase on the LHS would be K times BC, right?
Yeah.
And the increase on the RHS would be K times B plus C plus 1, because just look at the terms in which you have A, this term, and this term. So this would increase by KB, this would increase by KC, and this would increase by K. If you're increasing A by K.
Yeah, then the all over terms are increasing.
Yeah, like terms are increasing on both sides. Now the increase on the left side is KBC, increase on the right side is this thing. And now I just want to prove that this cannot be possible. Does that make sense?
Yeah.
Yeah, so the LHS always increases. Okay. Okay, so this is a slightly harder problem. But it uses the similar remainder concepts.
So we can write D as NA plus 1 and then N Q plus 1 and then proceed, I guess.
Yeah, you can write D as like, D is 1 mod N. So you can write it as like some NK plus 1. And yeah, so
Like here there are 3 variables, but we have been dealing with 2. So can we not somehow remove the third?
so it's that given any N, there exists a D such that this is true. Yeah, so you can't exactly get rid of a variable, but you can replace D with some NK plus 1. You still have 3 variables, but now it's easier to deal with. Like the one
E is
mod N
congruent to
condition.
1.
I have one
Yeah,
idea.
mod N. Yes.
Can you
Uh,
first explain what's, excuse me, can you please first explain what's that symbol after for all and before
Okay,
the,
this is there exists a D.
okay, thank you.
I had one idea, like we can write D is equal to NR minus 1,
Okay.
not D.
NR, it should be NR plus 1.
Hello?
Yeah.
What I'm saying is, we can do like N square A is equal to 1 mod D. So N square A is equal to let's say KD plus 1
N square. Okay, so you want to rewrite it as
KD plus 1
like this.
yes, and what
Okay.
we can do like
But how do you know that it's 1 mod D? You know that D is 1 mod N, not N is 1 mod D.
We are given that D divides N square A minus 1.
Okay, so you're writing it in this. Okay, fine. Sure, now what do you do?
and
Yeah, you can speak.
we can see the fact like T divides N square A minus 1 and also T is like 1 minus 1 mod N.
Yes.
I think I have a solution.
So we can write T as let's say NR minus 1
This is a different.
and like NR minus 1 divides N square A minus 1 and we can just do like NR minus 1 divides N square A minus 1 minus N square R square plus 1. Not R like T here.
Okay, some number.
Could you tell how we reached T is minus 1 mod A?
Because
Maybe you can write.
Actually, I said not A, I said N there.
Oh, you said N. Yeah.
PD is minus 1 mod A square.
Yeah, TD is minus 1 mod. Okay, but from this you cannot really say that.
Wait, we have NK plus 1 divides NE square minus 1. So
yes,
we add NK plus 1 to the RHS. So we get that NK plus 1 divides N square A plus NK.
yeah, but you can take out N because
Cut N because N is co-prime to NK plus 1.
yes.
So we get that it divides NA plus K. And now we subtract K times NK plus 1 from the RHS.
K times NK plus 1. Okay.
So we get that NK plus 1 divides NA minus NK squared. And now we can again take out N. So we get it NK plus 1 divides A minus K squared. And I think if you take N sufficiently large, NK plus 1 will become greater than A minus K squared. So we have that A minus K squared has to be 0.
Yes, so if N becomes really large, then that means that K has to become really large, right? Because A is fixed. So if N becomes really large, so we are assuming this is not 0. Let's first assume this is not 0. That might be easier. So now you're saying make N very large, right? So that means that this thing's absolute value has to become really large. And since A is fixed, K has to become really large. Now you still kind of have to deal with that case when K does become really large. How can you contradict that? Maybe try using something we got before.
Maybe you could use the same idea as last time. If you increase N by 1, how much will the RHS increase and how much will the LHS increase? And so that the LHS increases more. And then over time, as N becomes larger and larger,
you're using that in this expression or this one?
No, in the second one.
Yeah, but in the
negative.
second one, k can increase irrespective of n, right? Like the size of k is not really dependent on the size of n, and k can increase a lot. And you have a quadratic on the RHS, so you can't really control that. But over here, you have k is linear on both sides, so maybe try using something there here. Can you get a bound on k from this?
Yeah, we get that k is less than or equal to a. I think.
Oops. You can just split this in such a way that you take k out.
It says no equal to.
Yeah, so k is always less than, like as n gets really large, this becomes small. So you can always say that k is less equal k plus.
Oh, and then that solves the problem because then you
Yeah,
can see.
because k is bounded, so this thing is bounded. That means that as n becomes very large, this cannot go beyond a certain value. Right?
Yeah.
So yeah, you're done because of the size. So in both this problem and the previous problem, we used the idea of size, where something becomes really big, but the other thing is limited compared to that. So that's also an important concept in number theory in general, the idea of size.
How did you conclude that like k is less than or equal to a plus 1 from the previous step?
So the issue with this part is that when n becomes very large, then it's an issue because for that you have to make k really large. Otherwise, this thing becomes too small. Like this would become less than k plus 1. So this is saying that k becomes arbitrarily big. So okay, this may not be 1. You can even say like a by n. Okay, so to make it rigorous, you can just say 2a because this cannot be bigger than 2a. Like even if n is 1, this is just 2a minus 1. So the point is that k is bounded.
Okay.
Yeah, so here you're saying k is bounded, but here you're saying k is unbounded, which is a contradiction. So this must just be 0. That means a is a perfect square.
I
For
don't
some
understand the
reason.
fact that
For
a is
each-
equals to k square.
Okay, so for each n, you have some d, right? And each d can be written as nk plus 1. So that's like saying for each n, there is some corresponding k, right?
Yeah.
So now we got that nk plus 1 divides k square minus a. So if you, now n can be any integer, right? Because this is true
Right.
for all n. So you make n very big.
Yeah.
So now, and you know that k is bounded. So the RHS cannot be very big if you're making n large enough. That's why the RHS has to be 0.
RHS can be negative.
No, but the size of the RHS has to be very big. But for that to happen, K needs to be large enough because A is fixed.
Yeah.
Does that make sense? Okay. If anyone else has any questions, please ask. So if no questions,
How K is less than or equal to 2A?
just because of this, like here, the minimum value this can take is 1, right? Like if n is 2, this is 1. So this is just less equal to a plus 1. A plus a minus 1.
K is unbounded from a minus k square part, and we showed that k is bounded as k is less than or equal to 2a minus 1. How did we conclude that k is 0 from both these
No,
statements?
because, okay, let's assume that a minus k square is not 0, because we want to prove it's 0. So if you're assuming it's not 0, then we get that k is unbounded. But that is a contradiction. That is why k square must be equal to a.
So isn't a fixed for all n?
Yeah, a is fixed. K varies
K,
as n.
so if k varies, shouldn't a also vary as a is k squared?
No, we're saying that a is equal to k square for some k. If that is not true for all k, then k must become unbounded. Like we just need a equal k square for some k, because that just shows that a is a square. Okay, this is like a functional divisibility question, and you've had some functional equation class before, so that's more than enough for this. I just try similar strategies, but with these variables. And I try common things you would try for functional equations as well.
Divisible means fm by fn, fn minus fn divided by fm minus n is integer of f, or
Yes.
or fm minus n divided by fm minus fn.
This divides this.
Okay. I was just confused by this. Is there any trick to remember? Like from is divisible, divide, then divided. These three are always confusing.
If something is divisible by something else, then that means the divisible thing is bigger. Like if A is divisible by B, then B divides A. Like divisible and divides are like opposite things.
Okay.
When we say that fm minus n divides fm minus fn, then here also m is smaller than equal to n.
You can say that without loss of generality, I guess. Yeah. Like you can assume this and then try to prove for some another.
Like the first
Is
thing
this
we can
true for
No,
the
we need
first
to prove for all MN with FFM plus equal FFM. This is divisible by this. So you need to prove FM divides.
can we start by putting in values like m equals 0
Yeah,
and
sure. You can do that.
by the way, I had to ask one thing like no, remember. Sorry. By the way, can we just consider for this problem that f of m is less than equal to f of n, and then we prove that f of n is divisible by f of n?
Yes, for that and that. You can try doing that.
Yeah, so first of all, that means f of m minus f of n is negative, so we can just turn it into positive. Right.
Okay, write this as the other way around.
Yeah, that's why I asked the question.
Okay.
Also, I got one thing. Suppose we have f of we have f of n. Like we suppose we take m equals 1 and n equals 0 for instance. N equals 1 and m equals 0 for instance.
Okay.
Oh no, wait a second. Is it m minus n? No, take m equals 1 and n equals 0. So that f of m, so that m minus n is 1.
Okay. Say again.
Oh yeah. Okay. F of 1 divides f of 1 minus f of 0. So f of 1 divides f of 0.
Yeah, actually you can do this for any number, like f of anything divides f of 0. Like
Yeah. So
can you say that f of 0 is divisible by f of n where n is any integer?
yeah, that's exactly what we just did.
Yeah.
Okay, try more things like this.
yeah, we can say that. Also, like for example, no, like I was thinking that we could just we could just induct on this. Like if we take 2 and 0, no, we get that only, right? No. So if we take
Yeah.
2 and 1, yeah, if we take 2 and 1,
Okay, ns2 and ms1.
yeah, like yeah.
Okay.
F of 1 divides f of 2 minus f of 1, like that. Yeah, so f of 1 divides f of 2. So f of 1 divides all integers.
I think all the elements f of n or n is any integer, then all the elements has to be equal. Am I right?
Wait, huh? Can you repeat?
All the elements of the function are equal. Am I right?
That is not necessarily true. Like we're not asked to find the function. We're just asked to prove something about the function.
Can I say
Can't
that
we?
the function is constant?
Can you prove it?
Yeah. For prove the required condition, I have to prove this.
Can't we say that f of 0 is 0 because all f of n divides 0, f of 0?
All of them divide f of 0, but they don't have to be 0, right? Like it could be something else.
I mean, if we put m and n as 0, so we get f of 0 divides 0, so it should be 0.
No,
Right?
like anything
No,
divides
oh no,
0.
sorry, my bad.
Yeah, that's fine.
No, but 0 can't be infinitely large. Now we can make n large as much as possible. but
No,
0
but
is fixed value.
0 is the exception to that case. Like if
Acha,
you have something divide 0, that is okay. Like anything divides 0. That's how we define
No, I'm
divisibility.
saying about f of n divides f of 0.
Yes, but what if the function is constant? Then f of 0 need not be infected.
Excuse me.
Yeah.
Here we got that f of 1 divides f of 2.
Yes.
Similar by induction, we can get f of 1 divides f of 3. So by induction, we can say that f of 1 divides all f of n.
Yeah, we f of n divides all f of n. Also
And
similarly,
we
one
have also f of n divides f of 0. So we can claim that f of 1 divides f of 0. And also f of 0 divides f of 1.
Okay, you have f of 1 divides f of 0. Yeah.
Yeah.
I mean, I don't know if this is correct, but I'm getting that f of n divides f of kn for some k. Like k can take any integer value.
one
Yeah, that's probably the same induction as this, but you're just replacing
Yeah.
1 by n. Yeah, that makes sense.
can't we like take m as n plus k and we will get something like that? Like for example,
Sure.
if we can take m as n plus k minus n will turn it to f of k, and this will be f of n plus k minus no f of n minus f of n plus no. It won't be like that. It's something.
That's essentially the same thing. Maybe try to do something more with 0. Like you have f of n divides f of 0. Now, if you get f of n divides f of 0 plus or minus something, then you can say it divides the other thing as well. So maybe try putting in substitutions which give you something like 0 on the origins.
Um,
Also, it's from integers to positive integers. So as the m and n can also be like negative, you can put minus in. You can put things like that.
one thing, m or n can mean any integer. So why don't we try putting n minus 1?
Okay. Yeah, that's kind of what we did over here. Like we are like doing n and n minus 1 here. That's how we got f of n divides. F of 1 divides all f of n.
No, like the thing which I'm saying, f of 0, yeah.
Can we get something from this? Like we can say f of 2 divides f of 1 minus f of minus 1.
Minus f of minus 1. Yeah, you can do that. You're taking 1 and minus 1, right? Yeah. Okay, what if you put zero and negative thing, then you get f of some positive thing divide something nice. Can you try something like that?
Can you please repeat?
Like, so now what he just did is he took something positive and then something negative, but because you have m minus n, this thing becomes positive, right? Because you're doing minus minus. So if you do 0 and then minus n, then what you're going to get is f of 0 minus minus n, which is f of n. So try putting something like that.
So we will get that f of n divides f of minus n always.
Yes, because you have f of n divides f of 0 minus
F.
f of minus n.
Yeah.
And you know it divides this. So f of n divides f of minus n. What else can you say? Like something very similar.
Minus divides.
Exactly. Like you just put n as minus n, and then you get f of minus n divides f of n. So that means that these two have to be equal.
Oh, can they be the yeah.
Yeah, because if one of them is 0, then 0 divides something does not make sense. So also like the function maps to the set of positive integers. So these have to be equal. Now you can switch signs. Now you can try something nice with that.
I think by induction, it is a constant function.
Yes, this does imply that f must be constant, but you don't need to prove that. You just need to prove this case. But it doesn't imply that f is constant. It's just saying that if f of m is less equal to f of n, then you need to prove that this divides this. It does not mean it's constant. Like it could be something like a square or something like that. It not be constant.
I am thinking like putting n equals to m minus 1.
But are you taking your voice is kind of low?
N equals to m minus 1.
N equals to n minus 1. Okay. So then you're getting yeah, this is kind of what we did before.
As f of 1 divides f of 1, and from there induction follows.
Yeah, yeah. So yeah, we know that f of 1 divides all the like f of n, but that doesn't really seem to help us now. Also, like now since you have f of n is equal to f of minus n, if you have something like f of m minus minus n, this is f of m plus n, you get that this divides f of m minus f of minus n. But you can flip the sign of this, right? So you get f
We
of
have that f of 1 is equals to f of 0.
yes, that wait. Why is that? You
All
have one
f of
divides f
n
of
divides
0.
f.
Wait. How did you get that? F of m
Okay,
divided
so
f of m plus
like
n
you
minus
just take m plus n comma n. Like the motivation is you by flipping the sign you got this thing. But you can also like switch these two and get something very symmetric by taking m plus n comma n.
Okay, got it.
So maybe try to use some size idea here. Like you can also take cases on the size of f of m plus n.
The function has to be constant. I'm sure.
Okay, did you prove it? Like, it's not necessary to prove that in order to finish the proof. You just need to prove this property, which seems to be a bit easier to prove because you have these very symmetric things. So these three equations, they're symmetric in m and n plus n, right? So why don't we assume an ordering on the sizes? Like if f of m plus n is the largest among the three, then what happens? Like what happens to this expression?
That's not possible though.
Yes.
Yeah, makes sense.
Then the RHS has to be 0 if f of m plus n is the largest. So in that case, you have f of m equals f of n, which
That
is
was the
fine.
question.
Now, if f of n is the largest among the three, then what can you say?
If f of n is the largest, then the second cannot. The third cannot. Then
Yes.
if f of m is the largest, the second cannot. So yeah, it's a
Yeah. So if f of n is the largest, then these two have to be equal. So then the second one implies f of m just divides f of m minus f of n. So that just means f of m divides f of n. And similarly, if f of m is the largest, then you get the opposite way. Does that make sense to everyone?
Well, like what happens when f of n is the largest again?
Okay, if f of n is the largest, then this value cannot be larger than f of n, right? Because these two are smaller. Therefore,
Yeah.
this must be 0.
Okay. Okay. Got it.
Then you use the second one to get this. Okay.
Okay.
Minus m plus minus.
Sorry?
But if in the last divisibility, but if f of m plus n minus f of m is negative,
F of m plus n minus
f of m.
no, but like okay, you know that their absolute values are smaller than the absolute value of f of n. Like you're taking the size of their absolute value. Like anyway, you know that they're all positive integers. So if f of m plus n is some a and f of m is some b, then the size of a minus b cannot be bigger than something that's bigger than a and b themselves, right?
Yes, yes.
Exactly, that's what we're doing. So I hope this will be to everyone. The main idea here was to get something nice because we got this condition. We can sort of mess around with the signs. Then we got something very nice and symmetric. Like the moment you get this equation, then you think, okay, maybe I can get m on this side because you can easily do m plus n minus n. And then you get these symmetric things. And since you have symmetric things and you also have size constraints, it's a good idea to assume an ordering and try to think about each case. So I hope that was clear. Okay, we'll do one more problem. Just the floor function.
This one is so it's like I shared an approach in the group that I
Okay, if people have already done this, then maybe you can wait. If there are people who haven't tried this, you can try this.
no, like I have not done the problem. I have just did an approach which did work, I guess.
Can you repeat the previous one problem
Okay, so
quickly?
fine. Did you get that we got f of n is equal to f of n? Did you get that? Like, okay, so what we did was we first just put in some basic values, like we got f of n divides f of 0. And then using that, we put in f of n, we put in n and 0 and minus n. And then we got f of n divides f of minus n. And we got, and similarly, we can get the reverse. So that means that f of n is equal to f of minus n. And then we go here. And we get f of m plus n is equal to f of m minus f of n. Because this thing just becomes f of n, since they're equal. And then we get these symmetric things. We can also get f of m divides this by putting m plus n and n. And then when you get these symmetric things, you assume, say, what if f of m plus n is the largest, then this becomes 0. And then you have f of m equals f of n. And if f of m is the largest, then this becomes 0. That means f of m plus n is equal to f of n, and then from this you get f of n divides f of m. So in each case, you get the thing you want according to the size. Okay.
Yeah, for this one, what we can do is put n equals k square.
Yes, that's a good idea. So since this word variable is there, just put n equals some case. You put this as some variable. Like you can put floor of n as some k. Then you know that n is like right above k square. So you can let n equals some k square plus m.
Yep, n equals k square plus m.
And k plus 1.
And if you do that, you will be getting that k square plus 2 divides y square minus 4y plus 5. And after this, I'm done.
Okay, wait. What are you putting in?
K square, one side. Yeah, k square plus 2 divides m square minus 4m plus 5.
Wouldn't it be better to write this in terms of k?
On simplifying, we can get that k square divides m square minus 4i plus 5.
Wait, are you expanding in terms of k and m?
I just simply write k square plus m equals to k square plus 2 plus m minus 2 whole square. So the a square plus 2ab term will be cancelled and m minus 2 whole square plus 1 will be only left.
Wait, can you repeat? Are you using the same thing?
Yeah.
Okay. Now you're subtracting something?
Yes.
Okay. Times what? K square. Is this what you're doing?
Yep.
Okay.
Again plus 2 into 2m minus 2 minus 2 into 2 minus 2.
So you're doing this.
Yeah.
Okay. Is
Yeah.
this what you're getting?
Yeah, this is what we do.
Okay.
Yeah, from this how to proceed. Like I tried induction from like no, one thing we can tell is that m is less than 2k. So less than equal to 2k. So we can
Okay.
put m equals m is we can have two cases. M is less than k, m equals k, and m is greater than k but less than 2k. So we these three cases we can do, I guess.
Okay, so yeah, we know that n is less than k plus 1 square. I think you're using this. Because the float functions, k is the float function of root of n. K plus 1 square has to be more than n. Otherwise, the float function will be k plus 1. That's how we're getting this. So we get m is less than 2k plus 1. So m is less equal to k. So are you using that here?
Wait, from here we can write that k squared is less than or equal to m square minus 4m plus 3. And then m square minus 4m plus 3 is m minus 1 times m minus 3. And we know that m is less than or equal to 2k. And this expression is less than or equal to, oh, that doesn't give us anything useful.
By the way, m equals 0 case is trivial. There is no solution.
Okay, yeah, that's true.
Yeah.
Can we bound this between two squares?
We can find.
I think it should be possible.
Yeah, that is sort of the idea.
Can find the maximum value of k by finding the
Yes,
maximum
yes.
value of a minus 1 into
Not exactly k, but like the factor by which this divides this. So we can write this as m minus 2 square plus 1, right? And we know that m minus 2 square plus 1 is less equal 2k minus 2 square plus 1. Because m is less equal to. Right. And we know that.
Minus 8k should be there, I think.
Yeah, 8 will be.
Yeah, 8. So now can you take different, so now just consider, can you take cases on what this can be?
Yeah, like from here, what you're telling from here, like, how do you get 4k square minus 8k?
Like, you know that m is less equal to k. Did you understand that part?
Yeah.
So you just put it in here, right? Like you wrote this as in this form, so you can isolate m.
Yeah, that works. So I got this, but from here also it's a little difficult. Like from here you get this as well.
Yeah.
But the thing is, this will have no solutions. I checked. This will have no solutions. But the thing is, we can't guarantee anything about the previous m's. Like here you put m equals to k, but you can't guarantee anything about the previous m's. This will have no solution.
No, like you can just bound the size of L. Like you can say this is L is less equal to this. Does that make sense?
Yeah.
Yeah, so you can only have a few possible values of L, and then you can check them and do some modular things. So like clearly L can only be 1, 2, 3, right? Because if it's
What was L again?
like L is just okay. Let L be m minus 2 whole square plus 1 divided by k square plus 2. Take this as your L, and you want to bound this. Now you know that L divides, you know that k square plus 2 divides this thing, and this is bounded. So now L
Yes.
is bounded.
I have an idea that 3k square minus 4k plus 3 is the maximum value of this is 0. So then by solving quadratic, we have that the maximum value of k is an complex number, and then we are done that there is no solution to k.
Wait, how did you do that?
Yeah, I find this that k square plus 2 is less than or equal to 4k square minus 4k plus 5.
Okay. So what are you getting?
Minus 8k.
This,
I
right?
think you said minus 4k.
Yeah, this should be 8k.
Yeah, 8k.
Okay.
Then by solving the quadratic, we get that k is an imaginary number, a complex number.
For okay, you don't really need that. That is one way you can do it, but you don't really need to do that. Like from here, it's just 3 cases. It's not hard to check. So if L is
And by this statement, we can say that there is no values of k satisfying this.
yeah, that is true. Okay, so if k is 1, then we have k square plus 2 is equal to m minus 2 whole square plus 1. And if we cut the 1 here, then
Like
we just get this.
How do we know that like L is 1, 2, or 3 only?
Because L, we got that L is less equal to this. Is this fine?
Yeah, this I understood, but how is it
Yeah,
only
now
one
if
thing?
L is 4, then you get like 4k square plus 8 is less equal this thing. That's too big.
Okay.
That's fine. Okay, so if in the case where L equals 1, you have this, but this is like two squares, the difference is becoming 1. And that's not possible unless the squares are 0 and 1. That's really not the case. If L equals 2, then you have k square plus 2 times 2 is equal to m minus 2 whole square. This is 2k square plus 4 is equal to m minus 2 whole square. Now here, you know that k square must either be 0 or 1 or 3, right? So, okay. If k square is 1 mod 3, then this becomes 2 mod 3. And this whole thing becomes 0 mod 3. Which means this must be 0 mod 3, but then this becomes 3 mod, this becomes 0 mod 9, right? So if we look at this mod 9, what can k square be mod 9? It can be 1 over yeah, so is it none of these cases become let be LHS be 0 mod 9 in this case. And if k is 0 mod 3, then we get LHS as 1 mod 3, right? Okay, wait. I think something is wrong here. Yeah. Yeah, so okay. Now, since we do have a 3-year, it is kind of motivated to take mod 3. So if k is 1 mod 3, this whole thing clearly becomes, this becomes 2 mod 3, right? But a square can't be 2 mod 3. And if k is 1 or 2 mod 3. And if k is 0 mod 3, then this becomes 3 mod 9. Does that make sense? Because k square becomes 0 mod 9, this thing becomes 3 mod 9, but again, a square cannot be 3 mod 9. I hope that makes sense. It's just like checking cases at this point. And similarly, in the other case, you have 3 times k square and minus 2 square plus 1. And again, checking mod 3 works. Because this is 2 mod 3 and this cannot be 2 mod 3. I hope the last part made sense. It was not that clear. So essentially what we did was we put in a variable for the float function, and then we know that the gap between k square and n must be really close, and that gap is bounded. And from there we got a bound on this divisibility condition, from which we were able to just extract a few cases and check them. So I hope this much was clear for everyone. If there are any questions, please ask.
Yeah, it's clear.
So if nobody else has any questions, I'll be stopping now. And there are some more problems which I can either put in the future key set, or if they were already in the previous one, I can give you the sources if you would want them in the next key set. So I hope you enjoyed the class and thank you for attending.